Okay, so this lecture is meant to go over the concept of magnetic force. We introduced the idea of magnetic fields and where magnetism comes from. And so magnetic forces essentially are exerted whenever there are two magnetic fields in a given region. I guess it's two or more, right? So it's very similar to electrostatic force in that whenever you have two electric fields in a given region, then they'll interact with each other. So there is either a force of attraction or repulsion. So again, similar to electrostatic force. And some examples of this would be two permanent magnets attracting and repelling each other. So exerting forces. So this is the classic that you really in your daily life interact with when you've got two magnets interacting. Now remember, in the same way that you can induce an object to be electrically charged, you can induce a ferromagnetic material to have a magnetic field. So if you bring a strong magnet near a piece of iron that has those domains in it, you can then cause those domains to line up. So in a way, that's kind of like inducing a magnetic field in that iron object, and then it would be attracted to it. So that's our standard iron on our refrigerator. The refrigerator in and of itself is not a magnet, but if you bring a magnet nearby, then you can cause those magnetic domains within that material to go in a particular direction, and then there'd be a force of attraction. So two permanent magnets exerting forces. You could also have a permanent magnet and a moving charge. So remember that whenever you have a moving charge, that is innately where magnetism comes from. So a moving charge particle in and of itself has a magnetic field. And if you take that moving charge and put it in another magnetic field, then there'll be some forces exerted. Or you can have two moving charges. Can exert a force on each other. So you've conceptually visualized, or you know the two permanent magnets. I am going to show you a video a little bit later on about a permanent magnet and a moving charge. And then we really don't see the effect of two moving charges just because they're usually pretty small objects and we don't see them interacting with each other. But this is essentially how the Earth's magnetic field kind of compounds and gets bigger within itself, because you've got these moving charges and they create a magnetic field, and those magnetic fields will then cause other charges to move, and then those charges become a magnetic field, and then you just get this net magnetic field. So in the optional lecture for the Earth's magnetic field, I'll kind of go into that a little bit more. The strength of the magnetic force, I'm going to make sure my delineation's here. So the strength of the magnetic force depends on the strength of the magnetic fields. So it depends on the strength of the magnetic fields that are interacting. And that kind of makes sense. The strength of the electrostatic force depended on the electric fields that were interacting with each other. Another thing to understand is that magnetic force is an action-reaction force. Oops, maybe I could spell better. This is why I was a physics major. So this, again, similar to electrostatic force. Electrostatic force was an action-reaction forces. You could have a small charge and a big charge, but they exert the same force on each other. You can have a small magnet and a big magnet, and they're going to exert the same magnetic force on each other. So the force is the same. So the force on each object is the same. But the results vary depending on the size of the object. Oh my gollies, it's so hard to write with this pencil. I just want my whiteboard. So the results vary depending on the size of the object. And again, this is similar to every action-reaction force we looked at. Remember way back when in first semester, when we looked at like the bus hitting the bug, and we said that the forces on them are the same. Like when you're driving along and a bug hits your car, like the force that the bug exerts on your windshield and the force that your windshield exerts on the bug, they're the exact same force. But because your car has such a big mass, remember that Newton's second law says that net force equals ma. So the bigger the mass you have, the smaller the acceleration is going to be. The car, the windshield, doesn't really have a big effect, whereas the bug has such a small mass, it's going to have a pretty big acceleration for its size. So the same thing is true with magnetic force, in that you may have two objects that are interacting and the force on them is the same, but if you've got one object that's a lot smaller, it doesn't have as big of a mass, you're going to see the effects on it more so than the bigger object. And so this is kind of a discrepant event where we think, well, the smaller object moved a lot more, so it had a bigger force acting on it, when in reality, the forces are the same. It's just that the results are going to be different. And one other thing that I want to say is that the magnetic force, so a charged particle, moving in an external magnetic field will experience a force. We know that because the moving particle, let me be specific, the moving particle has its own magnetic field, and if it's moving in an external magnetic field, then we've got two fields interacting. So it'll experience a magnetic force that will cause it to move in a circular path. And this is due to the nature of how that force is directed onto the object. And so there's going to be an optional lecture that talks about what's called right-hand rule number 2, and that models how the magnetic force is actually perpendicular to both the magnetic field that's acting on the charged particle and the velocity that the charged particle is moving. And so the only way it can be perpendicular, let's say if you've got the particle moving in the x direction and the magnetic field that it's in is in the y direction, the force would actually be in the z direction. So that's a little bit different for us. And so that's one of the reasons why we're not going to go into that detail, is because it's a little bit harder to explain through distance learning. But the result is that it causes an object to move in a circular path, which kind of has some interesting applications, and it is helpful for actually determining the mass of these charged particles. So now I'm going to shift to showing you a video of a charged particle, an electron, it's actually an electron beam, and how it moves in an external magnetic field.
Welcome to the demo prep room. We're sitting here in the dark because we're going to show you that a charged particle beam does indeed go in a circle when you put it in the uniform magnetic field. So this is an evacuated glass bulb, and there's an electron gun in it. An electron gun really just means a heated metal filament that's easy to draw electrons off of. Near the gun, that you can now see glowing orange, is a little metal plate that we put at a large positive potential that sucks the electrons up to a few hundred volts at the plate. The plate has a hole in it so that some of the electrons keep going and form a beam that continues on until it hits the glass. Now you're seeing the beam because it's exciting a little bit of gas that's inside the bulb. You're seeing light from the gas, but it's there because the beam is shooting through the gas. So you're seeing the electron beam indirectly. Now we know that if we bring a magnet nearby, it'll deflect the beam. So here's my north-south bar magnet, and sure enough, one pole pushes it up, another pole shoots it down. If I bring it in and do these kinds of things, you can do all kinds of crazy patterns with the beam. You bring in a strong concentrated magnetic field. But what we're here to do is to create a uniform field. And that's what these two big coils are. This is a large coil of wire on one side of the bulb, large coil on the other side. So if you put them together, you can make a reasonably uniform magnetic field on the inside. So this power supply is going to increase the current in these coils, and we'll see what pattern the electron beam takes. So here, we're going to start turning it up, and you can see it's starting to curve more and more. And right now, it looks like it wants to make a circle, but the radius is too big, doesn't fit in the bulb. I'm going to keep turning it up, more and more current, bigger and bigger B field. Eventually, there it is. It makes a circle. Perfect circular motion, going right back to where it started. And if I turn the magnetic field back down to zero, straight again. So there's direct visualization of the circular motion of charge in the magnetic field.